Will Moody of Provectus, and the final presentation will be done by Mark Kluger of TRS. The presentations will be followed by a 25-minute question and answer period, but we'll start that off first with the panel discussion on how conceptual site models may change with the additional data of remedial action, and how do we deal with that. So without further ado, to give our speakers as much time as possible, I'd like to introduce Mr. Jim Cummings, our first speaker. Jim is the Technology Assessment Branch, works in the Technology Assessment Branch in the Office of Site Remediation and Technology Innovation at EPA headquarters. He has over 25 years of experience in development, evaluation, and deployment of innovative tools for the characterization and remediation of hazardous waste sites. Jim is a frequent and active participant in many forums, conferences, and seminars, so many of you may already know him. So with that, I'd like to pass the call over to Jim Cummings to present a federal perspective on innovative technologies.
Okay, thank you, Rick. Everyone, Rick, can you hear me all right?
Gotcha.
And the reason I included that fun fact for the Society of American Military Engineers was against the chance that any of you might have been involved in some point in your careers of installing a PSP strip, in which case I'd like to thank you because I never landed on one in my C-130 that wasn't successfully installed, so I appreciate that. Anyway, I've been doing this for a long time, and I'd like to share some of my thoughts and experiences at that level. And I think we need to go back a few slides because right now we're on slide 7. Again, even though the nominal topic of this discussion is combined remedies, I've included the words attentive, flexible, and adaptive in my title because that's as important as I'll get to in some of my slides. Next slide. Necessary disclaimer because I will be making a reference to some specific vendors and technologies. They're intended to be for illustrative purposes and obviously nothing that EPA would endorse. Next slide. And before we get into the combined remedies, for those of you that have been in this business a while may dimly remember there was a time when pump and treat and dig and haul was really about all we had to offer. So it's important for, especially for some of the newer folks, to understand that it really is a brave new world. And not only do we have a lot more tools, particularly the in situ tools, but we're doing a lot better job of controlling how those tools are applied and how they're operated. We're also, we've got a much better understanding of the subsurface than we once had. And I've got a slide or two that'll elaborate on that a little bit. And again, despite the fact that we model a homogeneous isotropic environment, the real world is anything but that. And the more that we can incorporate those realities into our designs and implementation, the better chance we are of succeeding. Everybody knows nobody wants to spend more than they have to on characterization. Joe Quinnen from Arcadis came up with a nice phrase or line of return on investigation. Hopefully the return is positive, and that's what you can use to sell spending a little more money on characterization. I would like you to do. Also, even though high-resolution site characterization, I think, is a phrase perhaps originated in my shop, but where I take issue with the fact is that we still are making too many simplifying assumptions. So I think a better phrase is higher resolution, which is certainly better than the day when all we could do was punch or put in monitoring wells with 20 or 30-foot screens. We now have direct push tools, and we now have HPT tools, which can give us a lot more information to characterize the site and probably reduce the uncertainty that we're dealing with. Next slide. And again, every conference I go to, I find a different vendor who's trying to work toward this goal. And that is the idea of having real-time or near real-time process control. Number of companies out there working on that now, and I'm hoping that they're going to finally deliver some things that can be used routinely by the average practitioner. With cheap sensors, telemetry, the increasingly cheap computational platforms that we have to work with. And actually at a recent conference, there was even some folks promoting the use of drones to help monitor the implementation of remedies and adapting as the situations dictate. Next slide. Again, combined remedies, I've been promoting this idea now for, I don't know, 10 or 15 years. I've been pleased to have put on conferences around the country with the National Groundwater Association. And more recently, we put on some webinars in New England with the New England Waste Management Officials Association. Every time I go to a Battelle conference, it seemed like there's an additional increment of presentations where they don't just try to use one hammer, but rather are trying to apply a variety of tools depending on what the site is offering. Also, my next slide, I'm going to talk about our emerging understanding of the compartmentalization of the subsurface. And again, it's not for larger or more complex sites. At a conference at Amherst, Massachusetts, 4 or 5 years ago, a substitute presenter at the last session on the last day gave a wonderful presentation on a heating oil spill cleanup that he had done. And he had used 4 or 5 different technologies, and they were all sensible. It's exactly what any proficient practitioner would have done. There wasn't a single tool that he applied that he was doing just to generate more billable hours. So I was gratified to find that it's not just the large A&E firms who have some awareness of the need and ability to use more than one tool, but even a solo practitioner doing home heating oil spills got the message and got with the program. Next slide. Again, I thought it was valuable to talk about too much of what the work that's gone on recently or still going on. A lot of our models are still based on the 2-domain model, storage and transmissive zones. The work by Arcadis and others are now acknowledging that it's really of course, it's really a continuum of zones, but for purposes of wrapping our minds around the phenomena, the idea that there's a transmissive zone, which may have 90% of the flow and the contamination, a slightly transmissive zone that might have 9%, and then a storage zone where you really have only 1 or 2%. And that's where back-diffusion comes from. Again, I've been dealing with back-diffusion for a number of years. My preferred attitude, if you will, toward back-diffusion is that in most cases it's a speed bump. It's not a roadblock. It's something that has to be taken into consideration when you're developing your conceptual site model and selecting your remedial alternatives. Next slide. And again, this was until we had to modify the presentations because Bell is having to run the slides. I had these flying in, and the animation was too much for us to try to process. But anyway, I listed a number of the different combinations of tools that seem to be out there today. It's really limited only by your imagination. We now actually have a number of sites where, because of the differences in lithology and hydraulic conductivity, that they've combined resistive heating or conductive heating with a steam-enhanced extraction. The first 2 are for the low permeability zones. The last is most suitable for the zones where you have adequate permeability to get steam distribution. Just about any remedy today, I'm sure those of you who've been in the business more than 5 years immediately think of bio as eventually being a component of the remedy, and I think that's being borne out by the experience that we're seeing, again, as you go to these different conferences. One in particular that I wanted to mention, 2/3 of the way down the slide there, the idea of combining in situ chemical oxidation with in situ chemical reduction. The ITRC did a document a few years ago in which they had a graph or a chart that suggested that ISCO and ISCR might be mutually exclusive. I know of 2 or 3 full-scale remedies where those 2 technologies were combined. In particular, for example, if you have a permanganate application where you're concerned about turning the downwater or down gradient water body and turning it purple, by doing some simple modeling, you can calculate the placement of your PRB in such a way that you don't have a passivation of one by the other. And then the last bullet slide there could be the subject of an entirely separate presentation. I presume most of the folks on the call will at least have heard about trap and treat, the idea of using carbon in various forms to trap a contaminant and then using either biological or abiotic additives to the carbon to then treat those contaminants. And if anybody who hasn't had a presentation from the Regenesis folks or one of the other carbon vendors, I'm sure you can find more information than you could possibly process on the internet. Next slide. Again, this is a very brief slide to point out that, as noted by the first bullet there, people have been talking about combining remedies since at least 1992. That was the first example that I could come across. And then Mark Zappi, the third bullet down there, who was with the Corps at Vicksburg for a long time, did some very interesting work 15 years ago on the idea of using a chemical oxidant to enhance the subsequent ability of using biological processes. So stoichiometrically, you don't put in enough oxidant to destroy the contaminants. You're just trying to get it to break down into smaller constituents which are sufficiently aqueous or dissolved in the dissolve phase for the biological processes to be able to finish off the job. Next slide. Again, 5,000, 10,000 foot level, there's two main ways. When I first started talking about this, again, back in the 2008 or so, we talked about either temporal or spatial variations on these themes, and they're pretty obvious. In one case, you have a treatment volume, you use one technology, reach a point of diminishing returns, and then transition over. Probably a more prevalent case for many of you practitioners is that it's pretty obvious, is to treat different zones with different technologies. So for example, if you have a strong source area, you're going to want to use a big hammer like thermal. Moderately contaminated zones, you transition into something like an oxidant or a surfactant. And by the way, let me go back a moment if I might. The idea of combining surfactants with oxidant is something that we've been somewhat interested in lately because I'm not a chemist, I'm an engineer. I think it's pretty well known that chemical oxidation, for example, is an aqueous phase reaction. So if you can get this, use a surfactant to increase the dissolution of the contaminants into the aqueous phase, the chances of your oxidant it's going to be effective, will go up. More recently, the idea of package deals, actually it's been around for about 10 years, that as opposed to having to have two different tools, perhaps with two different vendors and their associated overheads, you can actually use some tools that have more than one constituent of action. Matt Burns has written a nice article in Gwimmer that talks to this particular issue. Next slide. Moving right along. Package deals. This is going to be quick. Just some examples of some of the vendors. Keep going. Next slide. And again, the ChemOx vendors are morphing into Chem plus Bio firms. Next slide. FMC kind of led the charge back in 2008 with their Closure CR product. Next slide. TerraSystems has what they call SRS EZVI, which is a combination of biotic and abiotic mechanisms. This actually was developed by NASA and can be used to address some of the more unique contaminants like Freon. Next slide. And then Redox Tech and PeroxyChem both have agents that promote both reductive dechlorination and anaerobic bio for chlorinated solvents. And I think the last example I had was, next slide, please. The Provectus environmental products. In fact, I just got the flyer from the Provectus folks last week on their Provect Ox2, and I think Will may chat about that a little bit in one of his presentations. And the idea there, again, is they have both an extended duration ISCO component and then at least 3 years of enhanced bioremediation. Next slide. This is kind of teeing up Mark Kluger's presentation. Some years ago, Navy, Battelle for the Navy did a report looking at 5 ERH projects. And even though folks tend to think of ERH as a big hammer, next slide. Their report found that, in fact, they were seeing both enhanced bio and abiotic reactions at the temperatures and point. And I think Mark is going to talk about using lower temperature to encourage hydrolysis reactions for energetics. Next slide. And again, M&A, earlier I mentioned the idea of bio at the back end. M&A is just another word for that. And our guidance specifically provides that we think it's most suitable when you've done something about the source. Next slide. This is at one time was novel. By now it's pretty well established that M&A now is both biotic and abiotic. At a CERTIP BSTCP conference a few years ago, a DOD guy said, well, you know, we've got back diffusion going on here, but we're not seeing, we know it's matrix diffusion, but we're not seeing back diffusion, which suggests that the matrix itself may not be defenseless. There are processes and mechanisms, even in low permeability strata, which can help contribute to degradation of contaminants. And then I won't dwell on it, but biogeochemical transformation is the idea of using bioprocesses to potentiate abiotic reaction with metal species. Next slide. And again, the holy grail of any combined remedies is the idea of exploiting synergies. Both thermal and ISCO release a lot of dissolved phase carbon. I've got a slide on that in a minute. And I hope there's nobody in the community, practicing community, who isn't aware that the bugs really like temperatures in the range of 30 degrees centigrade. Next slide. Again, this is an example from TRS. I think Mark may have one of these as well in his presentation. The foreground is the initial dissolved phase carbon, and the background is the dissolved phase carbon after the remediation had occurred, and there was a 42% increase in that. Next slide. Again, as I said earlier, how you go about doing it is just as important as what you do. Two quotations here. I've been doing this so long. One of them is mine and one of them I stole. I just can't remember which. But the point is, because we can't punch enough holes, you're characterizing on 100 to 150 foot centers, and you're installing a remediation system on 10 or 15 foot centers. For heaven's sakes, take advantage of that. Next slide. An ACON webinar a few years ago, they were putting in an ERH system. They were putting in the wells to the top of rock. They learned that the topology of the top of the rock, which was dictating groundwater flow, was completely different than they thought. They were able to redesign and reposition their groundwater monitoring wells. Otherwise, it would have been useless. Next slide. And again, as for my money, I'm not a biologist, I'm an engineer, but I really think that the bioprocesses are particularly susceptible to change even during the remediation. And it sure seems to me to make sense to try to be as attentive as possible to the various conditions that are important in the subsurface. Next slide. Quick case study, and I know I'm almost running out of time here, but it'll be close. I shared this slide because at a CERTA BSTCB conference, some DoD folks were concerned that EPA was not being very flexible. I'm here to show you that this is a site where not only did we use multiple remedies, this was a rod, a conditional rod, in which we basically said, we're going to do resistive heating in the strongest part of the source, but we're going to do a pilot study and see whether ISCO or reductive dechlorination is preferable for the down gradient zone. Next slide. Again, this is an example in areas 1 and 2, we did resistive heating. In zone 3, we did some combination of resistive and thermal and ISCO. And then as you see down gradient there, there's some transects where we're using reductive dechlorination to try to anaerobically degrade the solvent plume. And then again, there was, because of the nature of the plume and the surrounding properties, there was also vapor mitigation going on. Next slide. So there's a couple of challenges remaining. One is predicting restoration timeframes, and we need better tools to QA, QC those representations. And as or more importantly, we need better rules than just asymptotic performance to decide when to transition between the remedial components, how much to heat, how much to eat. And when we do that, we'll be in a better position to really bring these remedies home in the most cost-effective way. I think I have one more slide. Kind of tries to characterize what I've said today and what I think the right remedial strategy is in this era of bigger toolboxes. So we want to use the robust technologies, but only as much as necessary. Next slide. Then we want to transition in some timely way to cost-effective polishing steps. Next slide. We'd like to reduce or eliminate the need for pump and treat. It's just not a very efficient way to, I understand the value of protecting human health and the environment by controlling plumes, but if you're trying to restore something, pump and treat is not very thermodynamically efficient. And then, as I said earlier in my remarks about M&A, we'd like to get to the point where we can have an appropriate level of reliance on M&A. And if you do the first 2 steps in that construct, the regulators will be very much more receptive. In fact, I try to work with PRPs that if you'll do steps 1 and 2, it'll make us much more receptive to M&A to polish things off. I think I'm done. Sorry about that, running over a couple of minutes, but I guess we're going to do questions at the end. Go ahead, Rick.
That's correct, Jim. Thanks a lot, Jim. Moving things along, just a reminder, if you have a question, you want to type it into chat, that would be very helpful. I'll write them down, and hopefully we'll get to them later in the presentation during the panel discussion and Q&A session. So let's introduce our next speaker. The fun fact is on the slide, but I'll give the serious fact. Mr. Will Moody is Director of Business Development at Provectus Environmental Products. He's been an environmental scientist with 15 years of experience, focusing primarily on in-situ remediation technologies to address soil and groundwater contamination. I've had the pleasure of working with Jim over the years in several projects, so he's got a lot of hands-on knowledge and field craft skills. With that, I'll kick it over to you, Jim.
Okay, thanks, Rick.
Will.
Everyone hear me?
Will, sorry. Yeah.
Okay. You can hear me. Well, good afternoon or good morning to everyone on the call. Thank you for joining us today. Next slide. So again, I'm Will Moody. I'm with Prevectus Environmental, and today I'm going to be talking about biotic, abiotic, and coupled solutions in about 15 slides. So as everyone can imagine, this certainly isn't inclusive of all the technologies. I tried to provide an overview of the basics behind abiotic, biotic, and coupled remedies, and then get into a little bit on the advanced side of the industry, what we're doing today as designers, implementers, practitioners, and looking at it from a few different slides. So again, I couldn't fit it all in, but let's jump right in. Thanks, Belle. So the first slide is, why do we even need to consider chemical oxidation, chemical reduction, and bioremediation? And I'll have some bullet points and some information that's repetitive to what Jim just mentioned. And I hate to pick on pump and treat, but when you start to look at some of these prime bullet points as to why the emergence of chemical and biotic technologies occurred in the mid to late 90s and are still being evolved today, we find that there was a desire from a cost, sustainability factor to either enhance remediation from a speed or be more effective on source or plumes, and then of course overall costs, whether that's O&M or long-term monitoring and ineffective technologies. So again, the emergence of ISCO, ISCR Bio, I would say, is because of speed, efficacy, and then overall cost. Next slide. And this slide sort of summarizes it in a busy fashion, where we have your chemical oxidants on the left, persulfate, permanganate, ozone, peroxide, and your chemical reductants, anaerobic, aerobic bio on your right. And so what you can see is that we quickly can fill our toolbox with other remedial options, whether it's ISCO, ISCR, or bioremediation. And there's certainly no silver bullets. Again, as Jim sort of outlined, a lot of these technologies, or I should say a lot of the projects where we're implementing different technologies, are going to be some sort of collective group of those options, similar to the case study that Jim showed. Maybe you're going excavation, and then you're going to use ISCO or thermal in the source, and then transitioning to a bio and M&A. So again, there's no silver bullets, but this slide is just showing that now we have a lot more options if an in situ technology is desired. Next slide. So I'm going to start with chemical oxidation and chemical reduction. These technologies mirror each other, whereas in situ chemical oxidation, or ISCO, is removing, the technology is removing, or the chemistry is removing electrons from your organic contaminants or your COIs, contaminants of interest. So these are non-selective technologies, so they certainly will interact with other organics in the subsurface. But ISCO, again, is the removing of electrons to destroy a contaminant. And then in many cases, you're getting complete destruction or mineralization. ISCR, again, is the mirror. It's donating electrons to destroy organic contaminants. Next slide. So I'm going to discuss briefly chemical oxidants, and then just one slide on chemical reductants. Again, I apologize for anyone that's on the call that was looking for specific technologies that I didn't have time to cover. Certainly we have some Q&A at the end, or you can reach out to me. I'm going to do my best to provide more of an overview. So when you start to look at chemical oxidants and really their oxidation potential, or the energy that's required to destroy organics, we'll start at the bottom with permanganate, MnO4, and as you move your way up, you'll see some very common oxidants that are used on a daily basis: hydrogen peroxide, persulfate, ozone, and then you get into the stronger oxidants that are really free radicals. This is really what we're trying to achieve in most cases for a best bang for your buck type of approach, where you're producing radicals, the hydroxyl radical and the persulfate radical. Those are those really strong oxidizers that again can destroy a wide range of different contaminants. Next slide, please. So I do have a little bit of chemistry in this presentation, and I'm going to start with permanganate oxidation. Unlike hydrogen peroxide and sodium persulfate, permanganate, whether it's sodium permanganate in the liquid form, and Jim mentioned purple, and so if anyone's used permanganate, they know it's purple. It can be almost black if it's really concentrated. The sodium permanganate, the liquid, potassium permanganate, the solid, it does not require activation or catalyzation to be effective. But again, it's a weaker oxidant, still certainly handled with care. But I'm just showing potassium permanganate here addressing chlorinated solvents, specifically TCE. And you can see it's complete mineralization to manganese dioxide and chloride. So I think one of the takeaways with oxidation is you're not going to get daughter breakdown products like you would with an enhanced reductive dechlorination. Now, the next two oxidants, hydrogen peroxide and sodium persulfate, typically are going to be catalyzed or activated in the subsurface. You're going to be producing those strong radicals. You can see here for hydrogen peroxide, it's being catalyzed by iron, ferrous iron, to produce the hydroxyl radical. So again, that radical is what is going to attack your organic contaminants, your petroleum hydrocarbons, your chlorinated solvents, your polyaromatics, for example. It's a complex reaction pathway, so you can also produce other radicals, the hydroperoxyl radical and the superoxide radical, which I'll talk about on the next slide. But again, we're looking for complete mineralization. It's carbon dioxide, water, chloride if you have chlorinated solvents. But it's important to note too that in some of your longer chain polyaromatics, you certainly will have partial oxidation. It's well studied. We know it occurs. So that could potentially be an issue, which is why you may need to have and I'll take this from Jim, a twofer or a threefer type of approach. Similar to peroxide, sodium persulfate would, again, most likely require activation. You're probably going to be using either iron or alkaline or heat or peroxide. I just picked two different reaction pathways or activation pathways. Sodium persulfate catalyzed by ferric oxide or iron oxide. Again, you're producing that sulfate radical, and in some cases ferrate, which is also an oxidant. And then alkaline activation. I saw a slide last week showing that I think 80 to 90% of all sites that utilize persulfate are being activated with alkaline conditions. So you're talking about a pH of 10, 10.5, or 11. Most likely you're using a caustic soda or sodium hydroxide. So you're handling a separate chemical. And again, there's other methods. Finally, ozone, again, doesn't require catalyzation or activation. And just like any topic I have in this presentation, we could spend probably 45 minutes on it. So again, just an overview. Next slide, please. Now quickly with the chemical reductants, again, I know there's others, zero valent iron, we can have 10 slides on, but I'm going to start with the superoxide radical, which is established but not well known. The first pathway or the first type of approach would be manganese catalyzed hydrogen peroxide at a neutral pH. Again, you're producing superoxide, so you're going chemical reductive instead of chemical oxidant. So you're actually using an oxidant to create a strong reductant to attack carbon tetrachloride, for example, or other compounds that may prefer to go reductive. Also, alkaline activated persulfate and manganese activated persulfate can produce superoxide radical. So again, you're using oxidants to actually produce reductants. So some interesting work being done there, or has been done there in the last, I'd say, 5 years. And then the main chemical reductant that I think everyone knows is zero valent iron. 25 years, if not longer, it's been used. The takeaway here is, again, it's reductant, so it's donating electrons. So if you see the elimination pathways below, where you have PC, TC, the majority of your pathway is going to go through beta elimination, where you're producing eventually acetylene and ethene. But you will produce 10, 15, 20%, you will produce some cis and vinyl, which don't react as well with zero valent iron. They certainly react, but it's just a slower reaction. So just be aware of that when you're evaluating ZVI and how your vendor or your contractor designed their program. Did they account for the additional pathway? Next slide, please. So again, I didn't have time to include everything for anaerobic bio or aerobic bio, and this slide will be very I think sort of basic as to what's going on the anaerobic bio side, specifically enhanced reductive dechlorination, where you're requiring some sort of organic substrate and you're creating an anaerobic environment, so a lack of oxygen condition, and you're generating hydrogen. That's your donor. And you're trying to overcome native electron acceptors to eventually get to what's going on below, where you're starting with your parent, your PC, your TC, and you're trying to go reductive dechlorination with microbes through cis, vinyl, and then ethene. Next slide. There's many organic substrates. I just listed just a couple here, but I'm defining them as soluble, slow release, and solid. Again, there's a lot of different versions out there, and so if you have additional questions on this, please contact me. Just some byproduct considerations. Nothing that's groundbreaking here. Obviously it's chlorinate solvents. You're producing chloride. You will produce acidity, which the microbial populations do not like. And again, there's a lot of different types of microbes out there. The most common that you'll hear to go all the way down to ethene is D. helicocoides or DHC. Typically after you establish reducing conditions, you'll come back and introduce D. helicocoides so they can attack your chlorinate solvents. Next slide, please. Also, just sort of the basics behind aerobic. Again, this is sort of the mirror of anaerobic, where oxygen is now the electron acceptor. You can apply it directly to the subsurface. Many times a calcium or magnesium peroxide is used. Unlike D. helicocoides, most of the microbes are ubiquitous. They're probably already going to be on site. Your contaminants addressed really range. Seen very uncommon contaminants try to be addressed with aerobic bioremediation, but typically you're looking at BTEX, your shorter chain PAHs like naphthalene, but then I've listed another few there. But the ultimate goal is complete destruction. I just put benzene there to water and carbon dioxide. Next slide, please. So those are some of the, I would say, the overview on your chemical oxidation, chemical reduction, and aerobic bioremediation technologies. Now we're going to get into the combined solutions, and this first one, again, it's nothing new. 2004, we're saying in situ chemical reduction. So there's a lot of different definitions for ISCR, but now I'm going to talk about ISCR as combining biotic and abiotic reactions. Jim had a slide on this as well. So we're trying to accomplish anaerobic bioremediation, and we're using zero valent iron as well. So it's a combined technology. So you're getting carbon fermentation, iron oxidation, very strongly reducing environments, and then a lot of hydrogen. So again, there's a few different technologies out there. I listed a couple here. And this is nothing new, but again, it's a combined solution that may be more effective in certain scenarios. Next slide, please. And this is actually, it looks like we're pulling several references right from NAVFAC, so thank you, NAVFAC. This is a standard enhanced reductive dechlorination versus in situ chemical reduction, parent to daughter pathway, or in ISCR's in the ISCR approach, trying to avoid any TC, DC, and vinyl chloride. Getting those conditions with ISCR is so anaerobic, reducing, and hydrogen rich, as well as abiotic with the ZVI, that we skip the enhanced reductive dechlorination process altogether. I should say we skip it while we're actually monitoring. Next slide, please. So some combined solutions. Also, Jim touched on a few of these. There are many, but I just touched on a few. Sodium persulfate being activated by ferric oxide. So again, you're producing the sulfate radical, strong oxidizer. In some cases, ferrate, another strong oxidizer. The remaining sulfate, which will be in all persulfate applications, so every persulfate application has this, can reduce. GTEC, for example, here I just showed benzene and sulfate going to complete destruction, and then also the remaining iron from the activation going complete destruction. Similar sodium persulfate and oxygen release compounds. I just stuck with the theme from a few slides ago, where you're combining alkaline conditions from the calcium peroxide or magnesium peroxide with sodium persulfate, and you're producing sulfate radical, potentially the superoxide radical, and the remaining sulfate can be used for bio. Also, you may have oxygen.
Hang on a second, Will. Could everyone please check to make sure your phone is on mute? Thank you very much.
Next slide, please. Thank you. I think this is my last slide for the afternoon. Just some other options to consider. Permanganate and persulfates being used. Keras Corporation has these in cylinders. People are also using permanganate to inject first and then catalyzing with persulfate. There's a lot of different versions of that. As Jim mentioned, sodium persulfate and potassium persulfate being combined for short and long-term ISCO conditions. There's a lot of different combinations, and it's really site-specific. And then also coupling in situ chemical reduction, and I'm referring to like either zero valent iron only or zero valent iron with organic carbon, and in situ chemical oxidation. So whether you're using ISCO in the source and ISCO as PRBs or permeable reactive barriers, or with the emergence of potassium persulfate, maybe you use ISCO in the source and ISCO PRBs in the down gradient. So you can flip and you flop, and you can mix these and match these depending on your site conditions. And then just one more, zero valent iron catalyzed peroxide persulfate. So again, a lot to consider. And then the last two, thermal source with sodium persulfate fringe, or maybe thermal just activating persulfate as a combined approach. Up at UMass Amherst last week, we saw a presentation where they're going to be using thermal to knock out the source, and then thermally activated persulfate for any residual. So a lot to think about there. And then last but not least, emulsified zero valent iron for DNAPL remediation. So another tool in your toolbox. So last slide, please, or second to last slide. Next slide. So just to finish up, just a few conclusions. Again, I apologize that I couldn't cover everything. I tried to sort of touch on some of the overview of the technologies as well as some recent advances. There are no silver bullets in this presentation. It's going to be very site specific, whether you're using one of these technologies or coupling these technologies. But I hope that now I've armed many of you with some other options moving forward to consider when maybe a traditional approach isn't desired, or access limitations or something like that. A lot of different coupled approaches. I didn't touch on undesirable post-treatment results, but that could also be a huge driver in how you select it. So you know that these oxidants or these reductants are appropriate, but how will the application affect your long-term source or plume management strategy? So something to consider for certainly 30, 40, 50 years of remediation and monitoring down the line. So just a few updates. Now we're seeing chemical oxidation integrated with multiple biological processes to address that speed bump rebound, and then slow release ISCO reagents, possibly for permeable reactive barriers, access limitations. But we're certainly developing new options, and we're trying to improve on the existing. So I didn't have, I couldn't certainly go through all this and include all the different technology names and who's got patents and licenses. So just so you guys know out there, some of these are patent and licenses, but as Jim mentioned, just cut and paste the technology on my bullet point and Google it. And I'm sure whoever's providing that technology will pop right up. So Google is your friend on that. So with that, just last slide. Thank you. There's my contact information. That's my direct line and my email. So of course, thank you for your attention.
Okay, thanks a lot, Will. Now I'll move forward and introduce our third speaker for today. Mr. Mark Kluger is a graduate of Johns Hopkins University. He's the Vice President of TRS Group and has more than 40 years of experience in analytical instrumentation, subsurface characterization, remedial technologies, subsurface geophysics, groundwater monitoring systems, bioremediation, and in situ thermal projects. Mark is another one of the circuit speakers who's been presenting at many conferences, workshops, and universities across the country over the years. And now I'd like to turn over to Mark, who's going to present fundamentals of in situ thermal remediation and heat-enhanced plume attenuation.
Thanks, Rick, and thank you for reminding everybody how old I am. 40 years experience sounds like a lot. I'm always the oldest person in the room unless Jim Cummings is there. Then I'm the second oldest person in the room. Next slide, please. Okay, so we're going to talk about in situ thermal remediation. Are expensive technologies. They work exceedingly well. It's becoming more and more popular. Essentially, there's three ways of applying heat to the subsurface. Resistance and thermal conduction heating are the two most popular by far. The third one is steam injection, which generally requires favorable geology. These technologies are significantly costly that people have been applying them to the source term, but over the years, as we've appreciated that heat helps reactions go faster, we're using lower temperatures with some of these compounds and substances that have been talked about, reductants, oxidants, and bio remedies to lower the cost of a combined remedy approach. Next slide, please. So why even consider heat in situ thermal remediation, ISTR? It's because of the robustness of the methodology. It works in rock, it works in sand, it works in clay, vadose zone, saturated zone. It's a very robust technology. It's fast, and we're talking about lots of mass removal in very short time frames. And interestingly, when you elevate the temperatures, you have groundwater that's moving through the treatment volume. Those elevated temperatures will help you down gradient. So here we have, we're applying a technology in a particular zone, but you get benefits down gradient as well. Next slide, please. So the sweet spot for resistance heating was primarily volatiles. For conduction heating, it's volatiles, semi-volatiles, PCBs, and PFAS, and I'll talk briefly about that a little bit later on. I think a question that may come to mind is if conduction heating will work on all these different things and resistance heating is just for volatiles, why consider resistance heating? And the answer is because if either technology will work for a particular application, resistance heating is likely to be less expensive, and you're going to get, again, more than 99% removal of the contaminants. Next slide, please. So here's some images that are taken with the same amount of energy put into essentially a sandbox. You can see with resistance heating on the left that we have uniform heating, and with conduction on the right, we have differential heating. On the left, we're showing we can get to boiling point of water. You have to have water or moisture in the matrix for resistance heating to work. With conduction heating, the great advantage is we can get to very high temperatures, but please remember that the maximum temperature of water is its boiling point. So if your goal is to get beyond the boiling point of water, it means you have to get rid of the water in the matrix. which may or may not be problematic. Again, it's going to be site specific. With our technology at TRS, we can get to temperatures in the matrix in excess of 400 degrees Celsius. That's pretty warm. Next slide, please. So with resistance heating, we take municipal power. It goes into a box that we call a power control unit. It's alternating current in and then alternating current into the electrodes. And it's the resistance of the formation to the flow of electricity that slowly raises the temperature of the matrix to steaming temperatures. And when I say slowly, generally it's about 45 days to get to the boiling point of water. But as this graphic illustrates, it works in rock, sand, silt, just does a vadose zone, saturated zone, it really doesn't matter. The goal is to create a phase change. We're taking the liquid and sorbed contaminants, we're putting them into the vapor phase, they bubble up into the vadose zone, where we have a blower package at the surface that pulls these vapors out of the vadose zone and then treats them conventionally at the surface. By conventionally, typically we're using activated carbon or thermal oxidizers to get rid of these organic compounds. Next slide, please. We do this work under buildings all the time. We can go in at very shallow angles. This is actually an active manufacturing facility in North Carolina. Next slide, please. So TRS, the company that I work for, has been doing resistance heating for something like 20 years now. And at the Battelle conference this year in April, we introduced a conduction heating element that is patent pending. We call it the flex heater technology. On the right-hand side, you can see perhaps that we have varying coil density, much like a slinky gives you variable coil density. And in our case, the slinky will fit inside a 2-inch well. Before, with the resistance heating, those electrodes were 10, 12 inches in diameter. Now we're talking about something that's 2 inches in diameter. And the wire, next slide, please. The wire that we're heating up inside that pipe, we can heat to really high temperatures, 1300 degrees Celsius. The energy transfer from the wire to the steel pipe is through infrared radiation. It's the same way your toaster oven works. So here, because this coil density is variable, we can have different temperatures vertically in the same pipe. And this is a unique capability. Next slide, please. So we're able to use resistance heating for some emerging contaminants like 1,4-dioxane. We've got a number of projects under our belt. And interestingly, we can use the flex heater technology for source removal of PFAS molecules. Next slide, please. So PFAS tends to boil off at less than 200 degrees C. And you can see here that at 350 or 400 degrees C, we have remarkable removal of these compounds. When we initially did our experiments at just north of 200 degrees C, we did not have very good recovery, and we're hypothesizing that that was due to surface chemistry interactions between these molecules and the organic carbon. But at elevated temperatures for about a 2-week period, you can see just remarkable mass removal. Next slide, please. We've applied these technologies in residential neighborhoods. That's our equipment compound next to a bank that had been a gasoline station. And our equipment compound, you can see, is sort of small. And then on the bottom right, this is a brownfield site in Lake Union, Seattle. Interestingly, they were putting in a subterranean garage at this space. And you say, well, why heat it up first? Why don't you're digging it up anyway? And the answer is we changed the classification of the waste and saved the developer a boatload of money. So that's a photo of one of our larger sites. Next slide, please. So I mentioned that we do work in Bedrock all the time. I think we have 16 or 17 sites under our belt at this point. And people say, oh, you've got DNAPL and rock. That's a tough problem. It's not an inexpensive problem, but again, we do napple in rock all the time. And in this particular case, in less than 3 months, we had more than 99% removal in a sandstone matrix. Next slide. So one of the things that we notice at our sites is we show up in yellow, we see lots of contamination. We apply the remedy in red, and we've gotten rid of lots of mass. But we come back to the site a year and a half or 2 years later, and not only did we not have rebound, but concentrations continue to go down. So something else is going on here in this source zone. And we're theorizing, well, these elevated temperatures are helping us out for some other polishing mechanism. So next slide. So we have an acronym, we call it a HEPA remediation, heat enhanced plume attenuation, and we define it as achieving sub-steaming temperatures to accelerate naturally occurring processes. And so bioremediation is one of these natural processes. Another one is hydrolysis, which is a water-based reaction. And interestingly, where we have lots of mass, generally stored in low conductivity systems, low permeability systems, there's lots of water in clay. Clay's about 40% water. It's not permeable, but it has high porosity. Well, if water is the reagent, we don't need to move it. All we have to do is heat it up. And so for those compounds that hydrolyze, we can go after them just by making, we can react these compounds just by making the groundwater a higher temperature, including the water inside the clay. When we increase temperature, we increase abiotic reaction rates as well with the soil or rock mineralogy. By mass transfer, I'm talking about essentially dissolving napple more quickly at higher temperatures, much like sugar will dissolve more quickly in warm water than cool water. Next slide, please. So this is a graph. Notice on the y-axis that it's logarithmic, and we're talking about temperature of groundwater here, or temperature in general. Groundwater temperatures in the United States, of course, are going to be much lower than 50, 60 degrees C. We're generally talking in temperatures from single digits, perhaps up to about 20 degrees C. So hydrolysis half-lives are not favorable for remediation at ambient temperatures. But look what happens when we start getting close to steaming temperatures, let's say 90 degrees Celsius. The half-life of RDX in a circumneutral condition is someplace around 10 days. Well, 7 half-lives is 99% mass conversion. So essentially, if I keep the temperature at 90 degrees C, which is below boiling, in, let's pick a number, 70, 80, 90 days, I've gotten rid of 90% of the RDX. And we have just been awarded a contract recently at the Sioux Army Depot, I think that's what it's called, in Nebraska, to do this on a full-scale basis. And that concludes my presentation. Thanks, everybody, for your attention.
Hey, thanks a lot, Mark. So we're actually doing really well on schedule here. So I thought what I would do, instead of having the panel, I'd like to start maybe with a few questions that come to mind. And I'd like to address the first question to Jim Cummings. Jim, you've got a really big overview of the industry and trends in technologies. You mentioned during your talk the toolbox, multiple technologies, combining technologies. What do you see? Is there anything on the radar that's out there that looks like a new breakthrough or a new technology that's developing on the horizon? Well, would that there were breakthroughs. Unfortunately, there haven't really been any that I would say were revolutionary. I will say with, and I know different people have different opinions about this, but I think the advent of carbon with its various amendments, and it's like I almost feel inadequate, because
after all these years of pumping gazillions of gallons of water out of the ground and putting it through activated carbon with all that thermodynamic inefficiency, why didn't I think of the idea of putting carbon in the ground 25 years ago? So there are uncertainties regarding carbon, just as there were and are uncertainties. For example, we've done a lot of permeable reactive barriers, but nobody's really sure how long they're going to last. So there are some uncertainties, including the longevity of this injected carbon. But I think that's probably as close to what I would call a paradigm shift as anything that I've seen in the last 20 years, certainly. Also, I will mention that I think we're becoming more receptive to, and Mark actually alluded to this, there was a time when if you were going to do thermal, the argument was you were going to put so much infrastructure in the ground, you might as well just beat it up with the heat and get it done, get it to whatever your cleanup levels were. But there seems to be more receptivity to being more sophisticated and looking at some of the attributes of the contaminants, and as Mark alluded to, possibly just taking it to a temperature where the hydrolysis rates go up exponentially. And that's where the cost curves cross, and you can actually save some money as opposed to putting in heater wells or electrodes on 17-foot centers. So I think that's about as close as I can think of as things that are dramatically different.
Okay, well, thank you very much. I have a question, a twofold question. I first want to present to Will, then Mark can answer it. Safety is a major consideration for all the things we do in this industry. And one of the things that comes to mind, I'd like maybe Will to address and followed by Mark, is what are some of the safety considerations of the technologies you deploy? How might it affect infrastructure, existing structures? I'd like Will, if you could answer that, then maybe follow up with Mark. He did show a slide that showed some heating under a building. So I'd like to get your gentlemen's input on the safety and infrastructure considerations for the technologies you're presenting.
Okay, yeah, that's a really good question. I could probably give you an answer that's 10 or 15 minutes long, but I won't. I would say that the first thing to consider is let's put aside the reaction properties of the different oxidants or reductants and the catalysts and activators. I think the first thing you want to find to reduce any sort of safety issues in the field is an experienced contractors, and that may be, you know, something everyone says, oh yeah, of course we're going to find that, but unfortunately, in my experience, throughout the U.S., you know, a lot of contractors have bid on work and they're not qualified to accomplish. And these oxidants and the reductants do carry, certainly the oxidants do carry some health and safety concerns. So I would say make sure the team that is combined to implement these technologies understands compatibility with equipment, you know, byproducts, whether it's carbon dioxide or heat, or you know, the reactions or the dangers associated with like a sodium hydroxide, things of that nature. So I don't want to get too specific on, you know, if you have a concrete cap and you have this or you have that, but I would just say make sure you have a very experienced team utilizing these reagents and understanding the post-treatment geochemical and other effects of the subsurface that could put you in a secondary groundwater issue state. So that would be my answer to that.
I'd like to echo
follow up on that. Mark, I was going to follow up real quick. I'm sorry, I was on mute. You know, one of the things that another comment on that is that a lot of contractors and consultants sometimes look at these technologies, at least in the in situ chemical oxidation area, and try to self-perform that work, whereas the contractors that do the work have the specialized equipment and safety equipment to do the work. And that's something I've observed in the industry, is some people say, let's self-perform. I think everyone has to ask themselves the question, are you really qualified to self-perform injections and that kind of handling those kinds of chemicals? And with that, excuse me for interrupting you, Mark. That point struck me as something I want to get across. So I'll turn it back to you, Mark.
Okay, well, thanks, Rick. And yeah, I echo both of your remarks. Certainly, experience is going to be something we should all pay attention to. At TRS, we're dealing with electricity, and as we know, electricity can have consequences that nobody would like. We spend an enormous amount of time not only training our people, but we have systems in place, redundant systems in place to protect not only our employees, but the general public, people who come in contact with our systems. We have infrared sensors, cameras, motion detectors. If anybody's unauthorized goes into one of our equipment compounds, the system completely de-energizes. We use isolation transformers to make sure that electricity doesn't leave our site. So safety is probably a bigger concern for us than for anybody else because our business depends on it, but it's singularly the most important thing that we do is to keep everybody safe.
Okay. Hey, I want to follow up with something, Mark. You made the point in your discussion that a lot of people didn't realize for many, many years is that we used to have the misconception that thermal technologies would sterilize the environment for bugs. I want to kick that back over to Will Moody. Is there a misconception or is it reality that when we put ISCO injections or ISCR injections in the ground, are we sterilizing the subsurface and making it more difficult for follow-on bioremediation technologies? Would you address that, Will?
Yeah, and that's I would say that's just a myth in the industry. Something that I've been just discussing for 15 plus years, where even when you're using exothermic and aggressive oxidant technologies like a Fenton's reagent or catalyzed hydrogen peroxide, you won't see full sterilization of the subsurface where some sort of follow-on or treatment-trained bio approach can't be effective. That's just certainly not the case. As groundwater flow comes back through that area, and it might be oxygen rich, you start to see those ubiquitous microbes flourish again or repopulate again. It's the same thing with like a sodium persulfate, strongly oxidizing conditions. We rely on actual post-treatment anaerobic degradation following sodium persulfate injection. And we have data sets showing 2 years of going from strongly oxidizing conditions, sulfate radical being produced, reductions of the contaminant mass, transitioning over time to anaerobic sulfate and iron reducing conditions. So I think it's a myth in the industry, and there's academic papers and external information out there to document it as well.
Yeah,
okay, well,
Rick, I'd just like to comment in all of our sites where we've applied in situ thermal remediation, we always see the microbes being active. Now, with D. halicocoides, that's a bug that doesn't do well above 40 degrees C, but once the temperatures drop below that, we see a big rebound in their populations.
Yeah, I know we worked on a project years ago when we were amazed at how the bio came back after the thermal application at an Air Force facility. I don't want Jim Cummings to be sitting out there not attended to. So, Jim, based on what we just discussed, a few things in terms of follow-up on thermal and follow-up on ISCO, is there anything, from your view from EPA that you've seen in the technologies where these technologies are compatible with bio and the treatment train?
Well, actually, the thing that one of my slides talked about synergies, the dissolved phase carbon, the thermal and ISCO send down gradient, and also the temperature. One of the things I suppose I would like to see more of would be the strategic coupling of those technologies. And by that, I mean, okay, you're going to do your thermal campaign and then specifically model and predict, for example, when the groundwater passing through the source zone that's been thermally treated should be reaching the boundary at about 30 or 35 degrees centigrade. And then plan to initiate your bio component for the dissolve phase to take advantage of that warm water. Now, I'm not saying it's going to be a tremendous cost breakthrough, but I think it's a meaningful way to reduce the cost of the follow-on bioremedy. And I understand that in many cases the owners are constrained. In fact, EPA has this problem as well. You just don't have the budget or the funds at hand to be able to do that in that timely way, and you have to phase your remedial stages as your cash flow allows. But again, the point is, if possible, in fact, there was a presentation at the Amherst conference 2 or 3 years ago where a company actually did that, and I think there's actually one going on now at a site out at Bothell, Washington, and I don't know, Mark, if that's one of your jobs or whether it's Cascade or McMillan McGee, but they're specifically planning to implement the down gradient bio in an effort to take advantage of both that dissolved phase carbon and the warm water.
Yeah, very good.
Yeah, I would like for people to be thinking holistically about their sites. You know, oftentimes we see our clients being focused on a specific operable unit as opposed to looking at the entire site at one time, especially when we're using heat and we have that benefit of the flowing groundwater moving these warmer temperatures down gradient. It'd be great if people would think holistically, not just what's going on in their specific OU.
Okay. Well, I wanted to kick into the panel here. One of the things that we've emphasized in site investigations remediation over the past several years is having a really well-defined conceptual site model. Jim alluded to earlier in the presentation, when do you end an investigation? We use more advanced tools in high resolution site characterization, things like that. And then you get the remedial design, the remedial decision, the technology you're going to apply, and then we put on contract firms that do these types of remediation, and we hand them our assumptions and our conceptual site model. And then when they start going in and doing the project, things may change. Financial decisions and contracts are already agreed to, and then we have the existing CSM, and then we go into remedy implementation. How do we improve the remediation outcomes, and how do you deal with the conceptual site model? In many cases, changes once you actually get into the subsurface applying technologies. And I know this is a point you're real interested in, Mark, so maybe I'll ask if you could open up some comments on that.
Yeah, so Rick, we see this all the time where somebody's spending a lot of money on a thermal remedy, and they have very defined treatment volume. And as we're putting in either our heater wells or our electrodes, we'll notice that perhaps on a periphery well or borehole that the concentrations are far higher than anticipated. So this, as you alluded to, this causes a problem. Contracts have already been let. There's a remedial design. People spend a lot of money by this point, and now the conceptual site model has changed. And the way I like to handle is having that conversation with my clients beforehand. That, hey guys, we're going to be putting in all these boreholes in the ground for electrodes or heater wells. The data density is going to go up in this specific region by orders of magnitude. What happens if we find something that's unanticipated? Let's have that conversation ahead of time, so when it does, or if and when it happens, we're prepared to deal with these new circumstances. It's not an easy problem.
Yeah, I mean, I just gave your firm a $3 million contract, and now we start doing the work, and then all of a sudden it's going to cost $4 million. And I guess the question is, do you put in place a contractual change mechanism? Or, I mean, we do a lot of work with performance-based remediation today. We do firm fixed price remediation, and some places there's guarantees of remediation. So how do you deal with that?
Yeah, so at TRS, we offer guarantees on about 75% of our projects, and people take us up on it for maybe 25 to 30% of our projects. So this is something that has real financial consequences, and again, we have to have this conversation up front that we're all dealing with the best information that we have at the time. It's not that anybody's not doing a good job. It's just the data density goes up so enormously. And so again, we have to have that conversation, and typically we have contractual language that stipulates if we find much higher concentrations than anticipated, those particular monitoring wells no longer are valid for the guarantee. So
Okay.
it's just a conversation we have to have prior to doing the work.
I want to, Will, if you may recall, years ago we worked on a project together where we didn't think we had LNAPL at the site. I'm not naming the site. I'm not naming the client. I'm just saying that when we had an extreme weather event, which is something we all need to consider going forward, and we came back after the site was flooded and part of a river, we discovered what was LNAPL when we had a technology application, which was for dissolve phase. Looking back, what unexpected? How do you deal with that? Our CSM just went out the door when we had a pilot study going in the field. Any thoughts?
Yeah, and Rick, you're not the only person I've worked with where we looked at all the information and thought we had dissolved only, and LNAPL popped up. So it happens, and a lot of lessons learned from that project was maybe over a decade ago now. But I think putting the paper performance aspect on the side, I think it comes down to whether it's a vendor like myself that does remedial design and has technologies in-house, really looking at all the information from a fresh set of eyes when you're in the remedial design phase. And I know it doesn't happen if a contract's in place, if the work's already been bid before someone like Provectus gets involved, but we always take a look at as much site information as we realistically can and try to point out data gaps at that time and say, as Mark mentioned, look, technically the remedial investigation phase is complete. However, here are some data gaps that we feel need to be filled in. Here's the assumptions we've used to develop a scope of work. If we're going to go out there and it's a 25,000 square foot area, maybe we spend some time just digging up some additional information at the site to confirm those assumptions before we install a network of injection wells or before we go out and we apply $100,000 in reagents. So I know that doesn't help if a contract is in place and you're in the field and things pop up, but I think it falls on all the, as much as it should fall on the parties that are all involved in trying to have, myself as the remedial technology provider, the injection contractor or what have you, looking at all that data collectively and trying to say, okay, these are data gaps. These are concerns. How do we address those prior to field mobilization? And it can be tied into the field implementation remedial method budget. But yeah, when you start to inject and you've got a lot of sorbed mass and a pocket of LNAPL, or in your case, site was flooded, we have seen LNAPL in the past, and so it's a very difficult position to be in with all parties involved. So a lot of our clients get us involved very early in the process. So they're in the middle of delineation and investigation now, and they say, does this site look appropriate for one of your technologies? If so, what information do you need and what data gaps exist that might concern you? So again, that doesn't address the primary question concern you asked, but I think it's good to get some of your vendors and your contractors involved early if you can, and see what they need and see what they may point out, and when the fresh set of eyes are on that data and that site information.
Yeah, that's a good point, because you never know when you start injecting how the dynamics of the situation will change. Jim Cummings, is there any, from EPA, you guys oversee the PRPs, you guys have your own, you do the work and all that. How does the situation, what have you observed, or how have you dealt with the situation from an EPA perspective?
All right. In fact, I had a ready answer to that. In fact, I was going to focus on the fund lead sites. Those of you that do work for EPA probably are no doubt aware of the fact that our money is oftentimes comes in buckets and categories. So, for example, we have problems where regional managers say, well, I've spent the money that I had to do characterization. But because we've been burned so badly at so many sites because of our rigidity and our understanding of the subsurface situation, that our current ploy, and I don't mean that in a bad way, I mean that in a realistic way, is to do remedial design investigations. If we think that our original model is particularly deficient, we don't just blindly design and implement the model based on that probably outdated and erroneous conceptual site model. Now, obviously, it's funds limited, but I think at the majority of our sites now, our more experienced RPMs will undertake that remedial design investigation phase to try to address at least some of the obvious gaps in our understanding. But before we lose the audience today, I'd also like to mention one other thing that actually harks back to the question that you asked me at the beginning about breakthroughs. 5 or 6 years ago at the Battelle conference in Jacksonville, the bio conference, there was a session where a bunch of geologists were mad as hell and they weren't going to take it anymore. I was there. I had actually heard a guy before that say that he thought we were spending too much time on the chemistry and not enough time on the geology. But I was a big hammer guy at the time, and I kind of just filed it away. But the point is, I think that because, as I said in my remarks, we can't punch enough holes, we don't really have high-resolution site characterization. I believe that we should be spending more time, thought, energy in this whole area of trying to bring geology to bear, to understand our problem and design and implement our remedies. In fact, at the AEHS conference a year ago, I put on a panel where that's what we talked about, trying to do a better job of understanding the geology, or what's called the plumbing, to help you understand where the contamination is and where it's going. So I guess I continue to have hopes that people will spend the time and energy to try to do a better job of bringing geology to bear. And it also applies in the 3D modeling world, which is becoming increasingly popular. One of my concerns about that is that they're connecting the dots or their data points with kriging, when I think we should be bringing geology to bear to the extent that we can on that. And I'll put in a plug actually for a project that Ed Gilbert in my shop and Herb Levine, one of our hydros in Region 9, spearheaded to write a paper on environmental sequence stratigraphy. If any of you that are, if anything I've said in the last 3 minutes resonates at all, I'd suggest or encourage you to look up that paper and give whatever thoughts you might to, okay, how can I, because it turns out that there's an awful lot more geologists in this business than I had appreciated. So if you're a geologist and are frustrated by the fact that you don't think we've got the resolution that we need, I'd sure encourage you to try to think about how that practice could be elevated, the discipline could be elevated in a way that would improve our remediation business.
Well, Jim, as a geologist, I appreciate that. As everyone knows, these are multidisciplinary projects that require all the skill sets. So with that, can I have the next slide, please? We're getting close to the end. We have another slide. Yep, okay. Well, I want to take a moment to, thank Sammy for helping put this platform for this discussion webinar together. And just to note that this Sammy has a small business conference that's going to be occurring soon in New Orleans, Louisiana, from October 31st to November 2nd at the New Orleans Memorial Convention Center. It's a great venue. For those of you who may be attending, there's going to be an environmental committee meeting at 9:30 in room 219 at the convention center. Also, just a little note that another major event that Sammy has is the JETSI. I believe it's next year in May in Tampa, and that gets somewhat into more of the technical discussions on various areas of concern for the Society of Military Engineers. I really want to extend a warm thanks to our speakers and especially our attendees today for taking time from your busy day. So on behalf of the Society of American Military Engineers and particularly the Environmental Committee, we appreciate your time and participation. We really hope this webinar has been useful. And anything housekeeping, concluding remarks, Belle, that you may have?
We're good, Rick. Thank you.
Okay, so with that, then I guess I think you mentioned before there'll be a certificate available, and with that, I'll conclude the webinar. And once again, thank you very much for your time and participation.
Thanks, Rick.
Thanks, Rick.
Could the speaker still remain on the line?
They're dropping off slowly.
Okay.
I've heard it before, but it's sort of a while.
Hey,
Jim's still on.
Hey, Will's still on.